Hey, good afternoon, and welcome to the What's on Board briefing for SpaceX's commercial resupply mission number 19 here at the lovely Kennedy Space Center, America's multi-user spaceport. I'm Greg Harlan with the Office of Communication, and tomorrow's launch is scheduled to lift off at 12:51 p.m. from Space Complex 40 on Cape Canaveral Air Force Station, and will deliver more than 5,700 pounds of equipment and cargo to the International Space Station. Today we're going to hear from some of the people that have worked in the science realm that are going to bring up different experiments up to the space station. And if you have a question and watching us live on NASA TV, please send us your questions via Twitter at #AskNASA. So to begin our program, we're going to see a video from the International Space Station's Science Program Office. So here to share with us a little bit about the Science Program Office is Mr. Brian Dansbury, Assistant Program Scientist for NASA's International Space Station Science Program Office.
Thank you, sir.
Welcome.
Well, thank you all for being here, and thank you very much to the investigators that are going to be talking to us later about their investigations. I'm excited to hear about these things. But before we get started, I do want to just sort of paint the big picture about science on station right now. Oh, and I just learned something else, and this is going to be bonus points for you all. I ask you all at the end. There's a Death Star in the picture behind me, so while I'm talking, let's see how many of y'all can figure out where the Death Star is as well. All right, so this is the 19th resupply mission for SpaceX, and the Dragon vehicles have been important to us for science because they're the primary vehicle to bring those samples back down to Earth from the experiments we've done up on station. This particular mission, about 2,200 pounds of science-enabling upmass is going to take place. And that's going to enable about 38 investigations, 23 by my count, new investigations. And that all-important downmass is going to enable about samples from 54 different experiments to come back and be handed off to their investigators for further research when we get down here. November 2nd was kind of a big day for us. We at Station are now in our 20th year of operations 24/7 in space. And so that means, and for those of us of a particular age, it's an amazing statistic. Anyone 19 years of age or younger has never been alive at a time when there were not men and women working and living 24/7 in space. And it just amazes me anytime I make that. I like to pause and think about that for a second. We talk about the Artemis generation. That is the Artemis generation right there. Over those 19 years, we've done about 2,900 investigations on station. Those represent about 100 countries, 100 plus countries. And that's generated 1,700 scientific papers from the results of those things. And the benefits and stories of some of those, by the way, you can find. I'd like to recommend a publication we put out earlier this year, Benefits for Humanity. We put the 3rd edition of that out. And you can find that at www.nasa.gov/station benefits. And I recommend you do that. Over the 19 years that the station has been in 24/7 operations, we've really evolved from a platform to a fully functional, capable laboratory where there's experiments going on a wide range of things. We work on human health. We do basic, fundamental science from fluid physics, astrophysics to biology. And then, of course, we do tech demonstrations and in-Earth observations as well. Reason we do experiments in space has a lot to do with microgravity. Turns out that when you take gravity out of the equation, there's an awful lot of physical phenomena that you can take a look at. Fluid physics, for example. Suddenly capillary flow becomes the most important mechanism taking place there. You can take a look at the effects of surface tension. We all see the astronauts with the bubbles of water floating in space. That's controlled primarily by surface tension. And you're going to hear a little bit later that combustion is different in space. When you take the convection out of the equation, hot air rising, you get different phenomena that you weren't able to observe down here on Earth as well. Of course, you get the extreme environment of space as well. There's a lot of material science taking place on platforms outside the station, looking at the effects of the vacuum, radiation, of ionized oxygen molecules, for example, at the upper edges of the atmosphere and their effect on materials. But you also have the vantage point of being 250 miles up, circling the Earth, 17,500 miles an hour. Those astronauts experience 16 sunrises and sunsets every day. So the opportunity to do Earth observation is really key. Those pictures that we see sometimes when there's a hurricane threatening the coast that come down from station, just the beginning of what you can do. And you're going to hear another experiment today, looking down, hyperspectral analyzer as well. All right, before we get going, how many of y'all have figured out where the Death Star is, by the way? All right, for those playing at home, that's about at least half of our social media audience here. That's not too bad at all. All right, let me hand it back over now.
Let's do a few questions and answers for Mr. Dansbury. Wait for a microphone. We'll get one to you.
How big is the International Space Station in reference to this room or this building?
Well, if you can put it out basically over a football field, end to end, including the end zones. And the usable space you can think of as a 3-bedroom home. And that's what the astronauts are living in and working in for 6 months at a time.
How many people are there?
But 6 astronauts, 4 USOS astronauts are up there right now. They will be conducting, they'll be there for 6 months. They'll be conducting 200 or facilitating at least 250 to 300 plus experiments during their time up there. And that's another example of how the station has evolved over time. Early on, it may have been scores of experiments or maybe 100 experiments that they got involved with. As more facilities and more capability has gone up there, the number of investigations per crew rotation has increased. Yeah.
Hello, I just have a question. What happens if an astronaut gets sick or needs to come home? What's the process? Like, how fast can you get an astronaut home if they need some sort of medical attention?
Well, see, that's another connection because NASA has always looked at the station as basically being a proving ground for processes and technologies we need to do the exploration programs like Artemis, return to the moon, eventually move on to Mars. And so telemedicine, ability to have the capability to diagnose things on orbit. And the astronauts do get a lot of training in how they can do first aid and that sort of thing. And there is all those protocols for the month or so before they go up to try and prevent them from being sick while they're up there.
And some of the past mission sets that have gone up have addressed antibiotic, dispersal in space. I think that was CRS-16 or 15
Right.
did that one. So you'll see some of these experiments that go through are actually, they're trying to take the knowledge that they have there and they're, pushing it forward for future space, astronauts. So.
And you're also looking at the behavior of bacteria. What's their virulence? Is it a little stronger? Is it weaker? And as we have more capability to do that sort of molecular studies on station, we'll get even more information on that.
That's right. I'll go here in the first row.
I have a question. How do you prioritize what to send up in the resupply mission?
That is a very complicated process. Yeah, the station. Well, first of all, we have our international partners. So we have agreements with the international partners for the amount of time you can think of. About 20% of the research on station is done by the international partners. 40% is focused by us at NASA, and 40% by ISS National Lab. You'll be hearing about here in a little bit. So there's those kinds of things. But then within that, we're looking from a scientific standpoint for the national academies lay out 10-year periods of the kinds of research we want to do, and we try and target our fundamental research to doing that. We look at how we can help commercialization in low Earth orbit, and then from a NASA standpoint, we look at what are our needs for the exploration missions we want to do coming up over the next decades. Very carefully is the short answer. It's complicated.
Hi. With the commercial crew program gearing up here and the Crew Dragon and the Starliner getting ready, and probably more ability to send people up to the International Space Station, what kind of work are we doing to prep for the station to be able to handle that kind of launch progress?
Well, it's a busy time at NASA, and it's a busy time on station with more and more vehicles going up there. But this is all part of that moving to NASA as one of many customers, and it's that additional sort of goal that we have that maybe we didn't have previously of helping to commercialize low Earth orbit and helping to have more partners come up here. So we're learning more things. If you think about it, with 19 years of experience, 24/7 operations, we've learned a lot about how to handle spacewalks. With the last spacewalk that just finished yesterday, astronauts have been outside the station more than 58 days. 224, I believe, is the number of spacewalks that we've done. That's experience. Now we're gaining this experience of how do we handle all of this coming and going of vehicles. And so we're always very careful ahead of time. We want to make sure that there's no way that the software will work right, that you can eject it, and do all those things. And as each new partner is added, that's another corporate entity that has that experience of living and working in space, and that'll lead to commercialization, and then we can go on to the moon and move on to Mars.
Correct. We had a question back here.
Hi, Eli here for World of Engineering. So I see that there's an Easter egg on screen of a Death Star. Should we take that as a sign that NASA has future plans to build a Death Star?
I would take that as a sign that someone is excited about December 20th and the next Star Wars movie that's coming out.
Any other questions we have in the room?
So whenever someone asks you that maybe isn't interested in space necessarily, what is your first answer for someone that doesn't understand the importance of the work that NASA is doing?
Well, there are so many strings you can pull on that, because when you take gravity out of the equation, there are so many new avenues for research. Protein crystal growth is something that there's a lot of experiments on station over that, and what that is about, and there's so many drug companies looking at doing this, because you can grow these, you can crystallize these proteins, and that's how the scientists in that crystallized state begin to look at the structure of the proteins and figure out what the protein does and be able to come up with a drug to either help or hinder the performance of that protein if you need to. In space, without gravity there, they can grow a little more perfect with less irregularities, and a little bit bigger, and you can see a little more detail. So that's one example.
What you're going to be finding also with some of our other speakers, the application process of when we learn stuff in space and we apply that not only to our space exploration side, but we also take it and apply it to Earth needs. There is an application there. So for someone who may not be fully interested in it, you'd be surprised at how many things actually touch their lives individually that have happened in space. Any more questions we have? Frankie?
Charles Atkeison at military_flight. With the success of Bigelow module, are you going to see more modules similar to Bigelow going up to ISS in the near future?
Well, I do know that as part of the press release that was out this summer about further commercialization in NASA's plans, there is one portal left, and I believe there was talk of then having a commercial module and having bids on that. So, yes.
So that is going forward, and we'll probably see it maybe in the next year or two?
Yeah. I'm not privy to the timetable of that, and lots of things can get in the way of that, but I do believe that they're working towards RFPs based on what came out this summer.
Okay, we have time for one more question if anybody wants to ask Mr. Dansbury a question. Back here. Thank you.
Steve, next flight Horizon, or Horizon Space Flight. So we're going to have more crewed missions coming from here. Would the time the astronauts be on the station shorter, since there'll be more options to transfer people out?
Actually, our human research program has really recently put out plans to have more one-year type missions so that we can get more data on how the body responds to that long period of time. You remember Scott Kelly and the twins study that was done a few years ago. I think just recently we've talked about maybe making use of those private astronaut missions to have shorter 30-day periods, and then the typical time period up there is 6 months. So we're looking to get various data points along those lines. So having more ways to get the astronauts up and out does give us a little more flexibility to have those times, and you'll probably see a larger variety of times that the astronauts are up there.
So thank you, Brian, for sharing with us a little bit about the science mission. Yes. So in 2005, Congress designated the International Space Station as our newest national laboratory. And in 2011, NASA selected the Center for Advancement of Science in Space to manage and promote science and technology development aboard the International Space Station's National Lab. And we're going to see a little video that highlights that.
SpaceX's 19th commercial resupply services mission to the International Space Station is loaded with a variety of investigations sponsored by the U.S. National Lab. This mission includes investigations from life, physical, and material sciences, all with the intention of benefiting life on Earth. Let's get an idea about some of the investigations that are launching on SpaceX CRS-19. Over the past 3 years, Budweiser has sent a series of investigations to the ISS National Lab to evaluate the germination and gene expression of barley in space. This will mark Budweiser's 4th payload launching the station and builds on the company's previous experiments. This latest investigation will examine the barley malting process in microgravity, and results could have implications in food production both on Earth and in space. Rodent research investigations in microgravity have provided a critical tool for evaluating accelerated muscle wasting and bone loss. Insight from these space-based inquiries has led to breakthroughs in drug development for patients on Earth, as well as new ways to enhance astronaut health in space. Now, the Jackson Laboratory will be sending 40 mighty mice to the space station. These genetically enhanced mice lack myostatin, a growth factor that normally acts to limit muscle growth, resulting in mice that display increased muscle mass. The research team will evaluate the mighty mice in microgravity to examine the potential benefits of targeting the myostatin and activin signaling pathways to prevent skeletal muscle and bone loss. The National Science Foundation is funding an experiment from Case Western Reserve University that seeks to study flame spread at confined spaces. By doing studies in microgravity, where buoyancy is eliminated, researchers can better understand the physics of flame spread. Such knowledge could lead to better infrastructure design and improved fire safety codes to help prevent injury, save lives, and reduce property loss from fire. In 2019, more payloads launched the ISS National Lab than ever before, and crew members dedicated more time towards ISS National Lab research than any year previous, showcasing the increased demand to leverage this unique facility for valuable R&D not possible on Earth. To learn more about all ISS National Lab sponsored investigations on this mission, Visit issnationallab.org.
From the International Space Station National Lab, please welcome Dr. Michael Roberts, the Interim Chief Scientist for International Space Station U.S. National Laboratory.
Thanks, Greg. I'd like to thank Greg for that sterling introduction with my job title. I'd like to thank Brian for setting the stage for what ISS is about. My job is to introduce the ISS National Lab, and I've been benefited in that greatly by the great video that you just saw, and the young man who presented that video, Patrick O'Neill's over here on the side. So a round of applause for Patrick. Any of the tough questions go to Patrick. So a quick show of hands. How many of you in the audience here had heard of the International Space Station National Laboratory before you decided to come here today? That's pretty good. The ISS National Lab has been in existence since 2005. You heard Brian talk about the International Space Station itself entering its 20th year. The International Space Station National Laboratory, as I mentioned, was founded in 2005, and in 2011, the U.S. Congress decided to have a non-governmental organization manage the International Space Station National Lab with the desire to broaden access to space for anyone in the United States who had an important science question or technology demonstration that could benefit from access to that unique platform. So in addition to the great science that NASA continues to fund on board the International Space Station to specifically address science goals as we move beyond low Earth orbit and begin to revisit the moon, go to Mars and beyond, you also now have the ability to propose science that addresses science questions that are directly relevant to you or your company. So as Patrick highlighted in the video, you saw that one of those companies is an iconic company, Budweiser. Who would have thought that Budweiser had desires to go to space to study the way barley behaves in the space environment? Budweiser has plans to produce beer at some point off of Earth. What they're learning right now at the International Space Station are addressing fundamental science questions about the way plants respond to life off of Earth. These are questions that are important, obviously, to Budweiser, otherwise they wouldn't be funding that research. But they're also important to NASA itself in that we're learning to begin how to produce crops that can sustain us as we move farther and farther into space. You also saw highlights from Jackson Lab. You'll hear following me two of the principal investigators on that mission, Rodent Research 19, which seeks to utilize the space environment because exposure to the space environment accelerates some conditions which mimic human diseases here on Earth. So muscle and bone loss is a problem for the astronauts if they don't exercise and take drugs in order to help them mitigate the loss of bone and muscle density. You can also use that model in animal models to understand the progression and onset of diseases here on Earth and help identify how effective drugs are in combating those conditions here on Earth. You also saw some examples of other experiments that are sponsored by other government agencies. So in addition to NASA sponsoring research and technology development in space, the National Science Foundation has been working with the International Space Station National Lab to fund research that looks at the fundamental physics of fluid transfer, flames, and combustion in the microgravity environment. Essentially because in the absence of buoyancy-driven convection, you can better model the effects of other physical parameters that control the spread of flames or the transfer of heat or fluids in that environment. In addition to the National Science Foundation, we don't have experiments on this particular launch, but we also at the ISS National Lab work with the National Institutes of Health, who is also actively funding research in space to address medical conditions here on Earth. So with the discovery of the International Space Station as a research platform, we've seen an increasing number not only of other government agencies, but a multitude of companies that are interested in accessing that platform to perform R&D activities that are of interest to them. So in answer to that question about why do we go to space, I think first and foremost, we go to space because we're curious. We want to see what's out there, what's over the next horizon. But more importantly, we learn things in space that translate to benefit us here on Earth. And that's the purpose behind the ISS National Lab. And as we enter this 20th year of ISS operation, we're very excited about what the next 20 years are going to bring us, not only in low Earth orbit, but in the voyage beyond that. because we're learning more and more every day from our exposure to that space environment, living and working in that environment, that directly translate to benefits here on Earth. With that, I'd love to take your questions.
Great. Do we have any questions for Dr. Roberts?
Hi, my name's Lexi. In your opinion, what experiment that's been conducted on the ISS has been your favorite so far?
Oh, I have an hour, right?
He just said it.
So on this particular mission, love the mice. We've flown, this is Rodent Research 19, not all of them have been ours. NASA continues to fly missions, but every one of the Rodent Research missions informs us about the exposure of a whole organism to that environment, and that directly translates into medical knowledge here on Earth. The NIH experiments are doing tissue chips, so they're, instead of using an animal model, they're using tissue chips that model the function of organs in that environment. Those are very important. I'm a microbiologist by training, so anything that has to do with mold, spores, or fungus, I get a little bit excited about.
Who else has a question? Right up here in the front row.
Hey, my name's Derek. I teach a 5th grade class. A couple of my students had asked what the future is of NASA's presence on the space station in relation to like the commercial industry and other countries.
Yeah, as Brian touched on a little bit, there are multiple access points for anybody in the United States as well as the international partners to utilize the station now. So the International Space Station National Laboratory was designed for R&D support for other agencies, for other federal agencies, or for industry. There's also now 5% of that allocation that Brian was talking about that's available for purely commercial enterprise. So even if your focus is not research or technology development in that environment, you have the opportunity now to take your commercial questions to the space environment. So there are opportunities all across the board now, and as more and more what we call implementation partners, those companies that have expertise in developing hardware that operates in space, in flying the vehicles that take cargo up and back, who are going to be supporting the private astronaut missions that we'll be getting next year. There are a lot of opportunities out there now for any entrepreneur at any level to begin thinking about ways to get into that environment. At ISS National Lab, for example, we not only work with the large, iconic Fortune 500 companies, we also work with small business startups through incubator programs. So there are opportunities across the board.
Right over here.
My question was kind of to build on that. If there are breakthroughs or something really works for a company, is there any plans to scale that moving forward?
Very good question, and yes is the answer to that one. So the International Space Station itself operates, I think of it in the mode as a test kitchen. It's a great environment in which to test and prove principles of concept. It's not a great environment for manufacturing and making lots of something. But there are opportunities through commercial service providers like the Bigelow module, there was a question about it earlier, or other providers who are thinking about what the next generation of space vehicle is going to look like. So people are already thinking about ways to scale up production in that environment. There are companies that are working on additive manufacturing technologies that are already being demonstrated in that environment, in the space environment, both inside the shirt sleeve environment on board the International Space Station, as well as in actual low Earth orbit.
And to Dr. Roberts' point, the Kennedy Space Center is a multi-user spaceport, and what that means is we have a lot of partnerships with different commercial and government entities that all have the opportunity to become explorers. And they have different capabilities that they can bring to the ISS. They have different capabilities to bring to satellite technology. And so we're opening the aperture and allowing some of our partners to utilize this multi-user spaceport here in Florida to get those things that would not normally be able to launch off of the Earth. They now could come here and launch smaller rockets as well as larger rockets.
So bring your imaginations.
That's
Money
right.
helps, but bring your imaginations.
Alex from Today in Space. So with all the opening up the aperture, are you seeing a big influx of people coming on? Is there enough room? Is there a backlog?
It's not any more backlog than it was before. There is an increase in demand, but as there is an increase in demand, there's an increase in supply as well. Those things that I kind of slept through in economics class actually hold true. Prices are coming down. It's still not as economical as it needs to be, but access to space is becoming more egalitarian than it's ever been. With as low as a few $1,000s, you can fly a small satellite, so it's within the price range of elementary schools or even after-school programs now to fly their own science to station. And as more and more creative minds come to the table, we're seeing more and more innovative solutions that are going to continue to drive that cost point down. So right now, we're fully booked with everything we've got with our 50% allocation, but as we need more, NASA works with us to provide more. And we work very closely with industry to identify where future gaps are, where we may have choke points to try to address those.
As a student who has dreams, and dreams turn into ideas, if I was a student sitting in my biology class, how would I get my idea to NASA, and how would I potentially get that in space? I know you said money helps, but I'm very, very, very curious.
Can all my students stand up right now, right in this room? All the students that came out, my presenters. These are real students that have real science, international partners that are come out and are going to share with you a little bit of their technology. On CRS-19, we had 2 young folks from America. Both were highlighted for their, their technology and their innovation. Okay, so, to answer your question, NASA's open to these ideas because the next generation has so many more ideas than the people that have come before it, and we are always open to the idea of sharing, partnering, and allowing those younger space explorers to kind of get in with NASA.
As a student who doesn't have, tweet you or?
Yeah,
Tweet
I'm not going
NASA?
to give my personal Twitter address on national television,
Right.
but we can definitely get you an answer for that.
I've got it, and I can get it to you later, though. Yeah, so in addition to reaching directly out, one thing as a student, you're used to going out and having to pull the information in yourself. So go out and look and see what NASA's interested in and what they're funding. There are a variety of funding opportunities that are available there. Industry also has those, and they're beginning to increase in number and diversity. So coming from the biology side of the house, there will be opportunities through National Science Foundation, through National Institutes of Health to fund research in that area. If you're more interested in the engineering aspects and technology benefits there, you can talk directly to the implementation partners. These are the folks who operate companies now that are building the hardware to support those. And then if you're really thinking big, you can start, sending emails to Elon Musk. If you've had a chance to drive by and see Blue Origin, right? Don't forget suborbital. There's a whole lot that's about to happen in suborbital that's going to swamp everything you've ever seen before in a very short amount of time.
Okay, we got time for one more question.
Really quick, super good question. What do you do with the wastewater? What do you do with the wastewater and your bio waste while in space?
2 very good icky questions.
It's icky, but it's true.
It's true. It's very important. So the wastewater, yesterday's coffee is tomorrow's coffee, is kind of where it comes down to. So they're currently able to recycle about 93 to 95% of the humidity condensate and wastewater, the urine that's generated. Solid waste is thrown away. You can recover a little bit of water from it, but it's not worth the expense of having to get rid of the microbes and the other undesirables that live inside of that body. But in order to do the Mars mission, we actually have to increase that recovery efficiency a little bit. So several experiments over the next few years are going to be looking at tweaking that 95% water recovery up to 97, 98% with new technologies. Very good question.
So let's thank Dr. Roberts for sharing a little bit about the National Lab. So our next researchers are part of the Rodent Research 19 experiment. The goal of Rodent Research 19, also known as RR19, is to investigate a proposed method of preventing bone and muscle loss both in space and eventually on Earth, kind of what we talked about. So here to share with us is Dr. Se-Jin Lee, professor at Jackson Laboratory in the University of Connecticut School of Medicine, and Dr. Emily Germain Lee, professor at the University of Connecticut School of Medicine and chief endocrinology and diabetes Connecticut's Children's.
Great, thanks a lot. I'm Se-Jin. I'm the principal investigator for this project, which we're calling Sending Mighty Mice to Space. This is a collaboration between the Jackson Laboratory, the University of Connecticut School of Medicine, and Connecticut Children's, as well as, of course, the ISS National Lab. You've already seen in the video and also from Dr. Roberts that the focus of this project is a protein that we call myostatin, which we discovered many years ago. And we showed that myostatin normally acts to limit muscle growth. And the dramatic illustration of this was that when we genetically engineered mice to lack myostatin entirely, the muscles in those animals grew to be about twice the normal size, hence the name mighty mice. We went on to show that myostatin plays a similar role in other species as well. And so in the first slide here, this shows one example. This is a bull named Hotline, in which we first identified a naturally occurring mutation in the myostatin gene. And you can see how heavily muscled this animal is. The same is also true in humans. In work that we did with Marcus Schulke in Berlin, we identified a child who was very muscular and who turned out to make little or no myostatin as well. So all of this immediately suggested to us the possibility that drugs targeting myostatin, that is blocking myostatin activity, could be useful in a wide range of conditions in which muscle loss or muscle wasting is a problem. So these would include muscle degenerative diseases like muscular dystrophy, but also muscle wasting that occurs in people with cancer, AIDS, heart disease, sepsis, and so forth. Muscle loss, of course, also occurs in people who are bedridden and in the elderly who are oftentimes physically inactive. And one way to mimic that type of muscle loss is in microgravity, as you've heard, where you get the systemic loss of muscle because of the inability to bear weight. So the focus of this project is going to be to determine whether getting rid of myostatin in mice that we send to the International Space Station can prevent or at least mitigate the loss of muscle due to microgravity. And we're going to be taking two different kinds of approaches. One is a genetic approach, so we'll be sending the mighty mice themselves to the ISS. These, as I said, are mice that make no myostatin at all because of the genetic change. But in addition, we're going to be taking a pharmacological approach where we're going to be giving normal mice a biologic, an experimental drug that's capable of blocking myostatin activity and causing the muscle to grow. Now, this particular experimental drug also has another potential beneficial effect. And at that, I'm going to turn this over to my co-investigator, Emily Germain Lee, who will tell you about that.
Yes, so, sorry. This drug doesn't only block myostatin, it also blocks another molecule that's called activin. Thank you. Sorry about that. And activin is very important. It regulates bone mass. So what happens is if you block activin, you get increased bone mass. So you block myostatin, increase muscle mass, activin, increase bone mass. So next slide. The next slide. So what you see here are CAT scan images. This is actually called micro CT because you can see it really in a fine-tuned way. And on the top panel are bones from our mice that are just plain normal mice. But on the bottom panel are our mice treated with the experimental drug. And as you can see, the bone density has really increased dramatically. And so what we're going to do when the mice return to Earth from space is actually do this micro CT. But we're also going to use another imaging modality called bone density or DEXA scans. And you've probably all heard of these DEXA scans. They're used in humans all the time and are very accurate for assessing bone density. So what we're going to do is do these DEXA scans on the mice on Earth, and the astronauts up at the International Space Station will be doing these DEXA scans on the mice up in space. So Sagen has already told you that astronauts lose a lot of muscle mass. And as you heard today, they also lose a lot of bone mass. So really, what you want to do is to be able to improve both muscle mass and bone mass together in order to give the most benefit. If we could do that, it would really dramatically help the astronauts, but it would also help a lot of people here on Earth who suffer from really debilitating conditions leading to muscle wasting and bone wasting, or both. So in children and adults, there are lots of conditions that cause bone wasting, that cause muscle wasting, that cause both. But basically, all of them cause immobility. And when you get immobility, you end up getting bone fragility. And when you get bone fragility, you get osteoporosis, which all of you have heard of. And osteoporosis is bad because you end up getting a lot of fractures. And when you get fractures, that creates this cycle of immobility. The immobility leads to decreased activity. That leads to decrease in muscle mass. And you can see you get this vicious cycle between loss of bone and loss of muscle. So really, by testing this experimental drug, we are hoping to be able to test a novel therapeutic method of combating, really, both muscle loss and bone loss, not only in astronauts in space, but really for a lot of people here on Earth. Thank you, and excuse my hoarseness.
All right, let's take a few questions. Here you go. Yeah. All right up front.
Charles Atkeison with at military_flight. How often will the crews on board station have to take the medicine? And is it in pill or is it by syringe?
So that's a great question. So this will not be done on the crew, although that would be the ultimate goal. But for the mice, it would be given once a week.
Your vision, how do you have a vision for the crews once this FDA has approved it and it's gone forward?
So, I mean, that's a great question. So right now in mice, it's being given by injection. And this is most likely something that would have to be given by injection to get into the bloodstream. The goal ultimately, and this, who knows how far that would be about once a week. And you should comment.
Yeah, I think it's probably too early to say for sure. And as drugs get developed, there's lots of fine tuning to increase things like half-life and and you have to determine sort of what the therapeutic dose is going to be and so forth. So hopefully it would be something less frequent than that, but of course it's too early to say until it actually get there.
Does anybody else have a question? Right back here.
Hi, I'm Christina Rowland. I have a question on how the drug itself actually works as well. You mentioned stuff like with people in older populations and people who are bedridden and may not be able to exercise and stuff like that. I understand that myostatin allows you to create more muscle mass, but for those that are unable to move at all, will it still help them because they're still not moving, so is the body still incentivized to create more, that kind of thing, or is it mostly for stuff like that bull that is actually moving and still able and capable?
Yeah, that's a great question, and that's part of the reason we want to do the study. It's because we want to know what will happen in a setting like microgravity where you have lots of muscle loss throughout the body and bone loss, and the question is, in that kind of setting, can you actually recover that by giving drugs that will block this particular pathway? But we know that in studies in mice, mostly in mice, but there's some human trials going on as well, we know that in lots of different kinds of disease settings where you lose, for example, muscle function, you can compensate for that by blocking myostatin activity. So we know that it works in some settings, but microgravity really gives us a unique opportunity to look at it in this type of setting, which is most closely related to what you would see, for example, in the elderly.
Okay, we have time for one more question. Right back here.
Hey, my name is Zach from 9to5mac.com. I have a question. I appreciate how you're able to take this study and make it relatable for people on Earth. And so what I wonder as investigators, do either of you have personal experiences or things that motivate you to go down this path?
Well, I have invested a great deal of my life in taking care of children who have a lot of conditions that affect their bones. For example, brittle bone disease and various others, and they're totally debilitated. And as a result of that, they have not only broken bones repetitively, sometimes 100 by the time they're 9 years old, they have severe muscle loss because they can't do anything. You know, they're immobile, they're wheelchair bound or bedridden. And so I've really spent my entire career taking care of kids like this, and it breaks my heart on a day-to-day basis. But their bones may be broken, but their spirit's not, and they give it their all. And so, I'm personally invested in wanting to see this work. Same with kids with muscular dystrophy. They end up with, terrible muscle disease, but that ends up being bone disease, like I explained. So, really for me, if this would come to fruition as a treatment in humans, it would be a dream come true. I mean, it's something I think about all the time. You can ask, this is my husband, if you haven't guessed, but it's something I talk about endlessly. So I'm very vested in it.
All right, so let's thank the Lees for coming up here and sharing with us about RR-19. So our next scientists are part of the Aztec Sat-1 program. It's an investigation that demonstrates communication between a CubeSat and a global star constellation satellite network in low Earth orbit. And this is the first CubeSat built by students in Mexico that will launch from the International Space Station. So to share with us is Andre Martinez, the principal investigator, and Rosa Gonzalez. She is a student from OPA-EP University.
All right. Can you guys hear me? All right, so imagine, if you will, you're responsible for operating a satellite that's orbiting our beautiful planet, okay? And you need to track it and command it so that you can bring down data from it. And remember, the satellite's moving at a speed of about 17,000 miles per hour. You get an opportunity, or 2 or 3 per day, to see it from the horizon, and it's moving at that speed. And as it comes right above you, and from the second you see it down on the horizon, you can begin tracking it and commanding it. And then it comes right above you, and then it leaves you. And that takes about 3 to 7 minutes. So you get a couple opportunities a day, and that's it. You're gonna need a ground station or 2, but they're pretty expensive. I'm Andres Martinez. I'm a program executive with NASA, and I'm responsible for small satellites. And this comes at a huge cost to some of my missions. So about a decade ago, we started investigating, well, what about using infrastructure that's already in space, right? Like Iridium, like Globalstar. Why don't we see if we can perhaps use that and guess what? Have our data downloaded 24 hours a day, 7 days a week. So here comes, this gave us an opportunity to formalize our first spaceflight collaboration with Mexico through Mexico's space agency, and they assigned the responsibility of the project to OPA-EP. Rosa is one of the students, and she's gonna tell you a little bit about the project.
Okay, so can I have the first slide, please? So this is our CubeSat. It's an exploded view of our CubeSat. It's a 1 standard unit CubeSat. So it's a 10 centimeter by 10 centimeter CubeSat. So it's pretty small. You can see all the components. It has solar panels, which is pretty basic for any satellite. And you can't see it there, but there's an electronic board that we actually designed, and it's in charge for the communication with the Globalstar satellites. So it basically weighs about 1 kilogram approximately, so it's pretty small. And as they've already mentioned, having the opportunity to work with small satellites also lowers the costs, so it's great for universities that are starting to work in these projects. Can I have the next slide? So this is part of our team. It's part of the students and the professors that worked in a 2-year program to create this satellite. There are a balance. Well, there's a balanced number of women and men that contributed, so we're pretty proud of that. And there's also many areas that were involved. So we have a student that's filming, and we're creating a documentary for the entire process. And there's engineers, etc. So.
Okay, so as you can see, this is part of the team on that photo. So mission objective number 1, demonstrate that we can use the infrastructure already in space, that we can connect with the global star constellation and have it download our data. That's objective number 1. Objective number 2 is give an opportunity, a space flight project hands-on opportunity to the next generation. We do that here in the US. This gave us an opportunity to do it with students in Mexico, where the students are designing and they're building and they're testing and they're gonna be operating this small satellite in space that will be Mexico's first satellite deployed from the International Space Station. Mexico designed and sent to space a couple of small satellites in the 90s. They recently sent another one in, I believe in May, and this will be the second one this year. And so we really view this, I view this as the momentum that Mexico needs so that a new industry can start in Mexico. So let's go to the next slide. So here you can see part of the team also. They came to NASA Ames Research Center, and that's where we conducted all the environmental testing. Happy to say that the testing passed the first time. And let me tell you, some of these tests, like the thermal vacuum power management test, it's a 24-hour-a-day test, and it requires 2 engineers to be there the whole time. Those are not easy tests, and they don't always pass. And guess what? If it doesn't pass, you have to do it again, right? And so I'm happy to report that the thermal vacuum test passed the first time. The vibration test, shock and vibe test passed also, and a couple other tests. So I was really happy with the results. If we go to the next slide. The next slide now shows a couple of students at NanoRac's facility, also showing off that they had passed the final test there, the final verification. And after this photo, the flight unit was integrated with the NanoRac's deployer. Thanks.
All right, so I'm sure we have some questions for our guests. Who wants to kick it off? Right up front.
I'd like to know more about you and your involvement with this project, as well as the rest of the students that were involved.
Okay, so I'm a student of aerospace engineering at UPAEP. Undergraduate, okay. Yes. So I'm 21 years old, and for me to be participating in such a huge project was like only in my dreams. So it's actually like a great opportunity because it's also a new career in Mexico. So having being the first generation of students of aerospace engineering and having already built a satellite, it's like incredible. So it's like an inspiration for younger people who are pursuing STEM areas, and it's also like putting Mexico in a good place for the aerospace industry.
Thanks for the question. Rosa, you want to tell them a little bit about your responsibilities?
Yeah, sure.
What did you do in the project?
So I was the student leader for the mechanics and structure subsystem. So we basically prepared the satellite for the tests that he already mentioned, and we also created an assembly manual. So this has great value because when we have, hopefully we have secondary missions, then we already have a manual, so it makes the process completely easier and faster. So we also have the experience of a satellite, so it will be easier to work with one in the future.
Anybody else have a question?
How great has it been to apply the knowledge you're learning in school to something like a CUBE satellite, to not have to wait to the next job, to actually jump into it and actually use what you've learned?
Sure. So right now I'm actually taking my first class in satellite technology. So it's like a great advantage because I know basically everything they're teaching me. So I'm the A+ student, so it's great. And of course, you always learn better by practice instead of just like studying. So it's a great advantage, and I'm really excited to have it.
Great. How about on this side? We've occupied a whole bunch of, right back here.
What was the upfront cost to get started making a CubeSat, and like how would someone get involved in CubeSats, and like what do you have to do to, I guess, develop a process to get there, to deploy one?
Yeah, so this, all the costs for designing and building and testing the CubeSat, it was funded by the university. So we're really happy that the president and the vice president, they're visionaries. Many times universities would ask, what for? What would you want to, build something like this? What benefit does it bring my university? Unfortunately, some universities have that type of response. In this case, both gentlemen are visionaries and they see the value and they see the opportunity, and I was really happy that they were able to support the project.
What's the cost?
What's the cost? Yeah. Typically, this type of CubeSats, about $100K, just for the parts, right? Yeah.
But I would say there's probably various costs that are involved in CubeSat technology, depends on the complexity of it. So it could go anywhere, a larger range. And so just so you guys know, we're doing a CubeSat funding briefing after this one. So if you want to stay around, I'm just kidding. We're not. But it does. There is a big range for, depends on the technology that's involved.
That is a really good point. So depending on what you decide to use in your design, right? I mean, there's some, I don't know if you're familiar with the Raspberry computers. I mean, some CubeSats consist of that, which is very, very cheap, very inexpensive.
I know some YouTubers that might want to put a sat in space. I ain't even kidding.
Okay. A question right up front.
It's about to explode.
I was wondering what kind of data you were looking at for your research now that you're sending it up.
Yeah, so in this case, we're downloading telemetry. We're taking some measurements of the environment that it's going to be in. Also telemetry of the CubeSat itself. So.
Okay, and for all those that are on Twitter right now, if you want to do hashtag #AskTwitter or Ask NASA, we can go ahead and field some of your questions if you're out there and want to field a question. I saw one right up front. This will be our last question for our university folks.
Do you have a deployment timeline? Is there certain apogees that you want the CubeSat in? Very.
So we're being deployed from station, right? So we're gonna pretty much be in. So what they do is, I don't know if you've seen, but nanoracks, they point down, and we get deployed. So we're gonna be just under the ISS, at about pretty much the inclination that the ISS is on. Right? So they gave us a window between January and February, yeah. So which is very nice, because I've had CubeSats on station that spent a few months, up to 9 months. So it's all based on priorities.
And briefly, will your university have a live feed of the data that it's producing or relaying?
So UPAEP, I mentioned 3 times that Mexico has done this in its entire history. They're making a big deal about this, as they should. And so the university is having a big event tomorrow to celebrate the launch, as well as the Mexican Space Agency. And yes, I believe that they're going to be live on Twitter and Facebook and other social media events. And UPAEP, it's UPAEP. You'll find the information also on your page.
Sure.
Yeah.
So that was our last question for our 2 guests. But one thing I want to say is this is the face of future exploration internationally, okay? So a young person with a team of other great young people doing amazing things, just like in America, down in Mexico. And then we have other folks throughout the, the world that are doing, that are excited for, kind of touching base on what your question was. How do you get excited in space when you see young people like this doing amazing things? So thank you for having them come out.
Thank you.
So our next experiment is the HESU-E Hyperspectral Image Suite, a next-generation hyperspectral Earth imaging system and follow-on to the Advanced Spaceborne Thermal Emissions and Reflection Radiometer, also known as Aster, on NASA's Terra satellite. And here to share with us is Dr. Hakira Iwasaki, and he is the professor at the University of Tokyo and a principal investigator.
Thank you for introduction. It's my pleasure to be here with you. I would like to express special thanks to the JAXA team for providing us a chance to go to the space, and also to the NASA and SpaceX team for giving us launch to the space. Okay, why nature is so beautiful? Okay, first slide, please. You can see very beautiful bird in the picture. Okay, the bird live near clean water. The color of the bird comes from interference of light, acting as if it is a natural spectrometer. Hisui, which is named after the bird, is the imaging spectrometer for Earth observation. Hisui was developed by Japan Space Systems under the supportment of Ministry of Economy and Trade and Industry of Japan. Okay, next slide, please. Okay, we can see 3 primary colors under our eye. Those are green, red, green, and blue. And multispectral sensors such as Landsat extended the wavelengths they can observe for Earth observation. You can see in the right picture of ASTA sensor. That is a color ASTA sensor can observe. And ASTA is a long project between Japan and NASA, United States, using the spacecraft Terra, which was launched December 1999, about 20 years ago, and still working well. And you can see wavelengths between 2 and 2.5 micrometers. There are 5 spectral bands. That is very useful for mineral identification from Earth, from space. So the function of this ASTA for 2 micrometers, it is already broken. So Hisui is another sensor to succeed ASTA. And you can see hyperspectral example of Hisui at the left image. It can observe more than 100 spectral bands. Using this method technology, we can identify minerals and other things from space. And let's go to the next slide about the hyperspectral world. Okay, you can see the world is full of minerals. Minerals has its own specific absorption band in spectral. Therefore, using this signature, we can distinguish and identify minerals. Furthermore, we can notice and detect the subtle changes in absorption band. That comes from change in environment such as formation and crystallization. And using the map obtained by such sensor, such distribution of minerals are strongly related to natural resources. So in this sense, such sensor is a modern prospector. Next slide, please. In recent years, in arid or semi-arid area, the salt damage is several problems for agriculture. Hyperspectral sensor can obtain the image and data about salt concentration in soils, independent of soil types, using the combination of spectral band around 2 micrometers. Therefore, we can consider about countermeasures that will contribute to future sustainable development of agriculture in this area. Next slide, please. When corals are stressed by change in environment, such as temperature, they expel symbiotic algae living with them causing them to turn white. Coral bleaching is a problem in southern seas. Hyperspectral sensor can detect such changes using the power of spectrum, and we can determine and discriminate dead or alive corals. Using the floor map derived from hyperspectral sensor, we can make a map of corals for shallow water. And next slide, please. Okay, in central Kalimantan, large amount of carbon dioxide is emitted by wildfire in peat swamp forest. We should measure and report and verify amount of carbon dioxide emitted in this area by local government. Using hyperspectral data, we can estimate biomass and classify the peat swamp forest into primary and secondary forest. That is determined by local government as forest types. And furthermore, forest types found by this method is useful to evaluate biodiversity in the forest because of high biodiversity in primary forest. Next slide, please. Okay, hyperspectral data is also useful in agriculture. Using hyperspectral data, we can estimate grain weight and grain nitrogen contents by combination of not only primary 3 colors and near-infrared colors, but also some combination of colors that is very essential to discriminate some properties. So using such data, we can make some grain weight map. That is very useful for agriculture. And next slide, please. Okay, this is the same as field, and this is a case for pasture area. When you go to the pasture area, the color of leaves changes with grass species. So using the power of spectrum, we can distinguish the species of grasses in the area. Using the data, we can manage efficiently the area, and also we can judge the time for replanting the grasses. The final slide, please. So KSC will be launched tomorrow, and we're going to be attached to the exposed facility of Japanese experimental module. And at the exposed facility, there are several Earth observation sensors that are developed by NASA exist, such as OCO3 or EcoStress or JEDRE. We are looking forward to getting data of KSC and collaborating with them soon. And video, please. Okay, so this movie is also made by Dragon team, and so it is very interesting. The sensor developed in Japan is transported to United States and launched by United States rocket and attached to Japanese experimental module. Again, I'd like to thank all the persons who established such a great project in space for international collaboration. Thank you very much.
And we're going to go ahead and bring up Mr. Shoichiro Mihara, who is a mission manager on this project. And we're going to take a few questions. Does anybody have any questions? All right, back here.
To determine what the other planets, like the mineral content or whatever is on the other planets, will this technology be able to help us determine really what's going on there, like it does help us here on this planet then?
You mean that if a hyperspectral sensor will be used in the other planet, so it will give us a lot of information or not? Yeah, I believe it will give us a lot of information, especially there is a possibility to have water or some vegetables or something like that. So maybe not direct future, but in some future, spectrum analysis will give us lots of information.
Okay, right back here.
Awesome, thanks. What is the depth of penetration for this sensor? Is it just surface level, or how far below the surface can you look currently, and how far do you expect that to advance?
As for sensing, it is on the surface. But if there is some phenomena in the ground, so it will come out in the surface. So if we observe the signature on the ground, we can estimate what is inside and something like that. Of course, we cannot penetrate the spectral information, but we can get information out of the surface information.
Thank you.
I can add some information. So the minerals comes from the magma, and it penetrates the land, so it makes some concentric patterns. So there is a distribution of concentric pattern of minerals. With this, we can estimate not only the surface, but also under the ground.
Okay. We have one more question right here.
What's the resolution that this sensor will be able to produce, like its imagery? What's the resolution?
Okay, there are two resolutions. One is spatial. Spatial is 20 meters by 30 meters. And in spectrum, in visible range, 10 nanometers, and shortwave infrared, 20.5 nanometers. So that is the spectral resolution.
Okay, I have a quick question. So will this technology be able to help farmers determine when to cultivate crops or when to harvest crops?
Right, right.
Okay.
Yeah, it
so
will give us a lot of information to determine the when to crop.
Okay, great, great. Well, thank you for both these gentlemen for sharing with us their information. And arigato gozaimashita.
どういたしまして。
どういたしまして。
Thank you. All right, our last scientists that are going to be coming up are part of the confined combustion. And that's understanding how fire spreads and behaves in space is critical for the safety of future astronauts and for understanding and controlling fire here on Earth. So we have Professor Yating Liao, with principal investigator with confined combustion, and Dr. Furkul, co-investigator for confined combustion.
So our experiment is called confined combustion. So what we are going to do is we are going to burn some small fuel samples, solid fuel samples in a wind tunnel aboard the International Space Station. So why do we want to do that? Because we want to study how solid materials burn in different confined conditions and how fire interacts with its immediate surroundings. So you may ask why we want to study this. The reason is because we know that flame behave or fire behave very differently in open and in confined environment. So let me use a recent fire incident as an example. Can I have the first slide, please? So what you see here is the Grenfell Tower fire in London in 2017. This fire killed 72 people, so it's very fatal. So the fire actually originally started by a malfunctioning refrigerator on a lower floor, 4th floor, I believe. So the reason the fire was so fatal was because the fire spread unusually fast, right, from the lower floor to almost all the floors there. So what happened here is actually after, shortly before the incident, the building had gone through some renovation. So cladding were added to the building facade for energy and cosmetic consideration. However, this installation created a cavity space between the outer surface of the building and the cladding.
So when fire enters this cavity space, the thermal expansion of the combusting gases and the flow confinement accelerates, force the flame to accelerate, and so it spread way faster than usually seen. Also, the inner surface of the cladding may have reflect radiation back to the flame, further enhancing the burning. So, this effect combined pose serious concern for similar fire scenario both on Earth and space. This is why we want to study aerodynamics and thermal interaction between a spreading flame and surrounding wall. So you may ask why we want to study this, why we want to bring our experiment to microgravity environment in space. The reason is because we know that on Earth, hot gas rises, right? So fire is hot, so you unavoidably it associates with buoyancy flow. The problem about buoyancy flow is it varies with time and location when your fire grows, right? So it's really hard to characterize. And this complex flow may mask the underlying physics we want to observe. On the other hand, in microgravity condition, we eliminate the buoyancy flow. And instead, we can impose, like in a controlled manner, impose a flow externally. So this, So because of this reason, the benefits of bringing our experiment to microgravity environment are multiple-fold. First, as I mentioned, it eliminates the gravity, so it hence eliminate the confounding factor associated with the buoyancy flow. This greatly simplify our problem. Second, we can always have direct study of spacecraft fire safety issue. And third, the data will help us to have better and improved numerical model. Right. So can I have the next slide, please? So this, I think, do you call this fish eye view? Yeah, fish eye view of our experimental setup. So you can see that everything actually set up in a glove box. Later you will see more video image of this. At the center, you have a black box. That's our wind tunnel. So all the sample will be burned inside the wind tunnel. Okay, now Dr. Faku is going to talk more detail about our experiments.
Okay, thank you, and thank you all for being here today. So as Yating said, the heart of our experiment is that little black box in the middle. It's about the size of a toaster. And within that, we burn fuel samples, solid fuel samples of either a cloth-like material or a plastic thin sheet of material. So you see cameras, there's a camera above, and there's a camera looking at a mirror view to the front view, which is those are our chief sources of data, is actually flame imaging. And it's a small wind tunnel, so we actually force airflow past the sample, because without gravity, if you just left it burning, it would probably go out by itself, to be honest. So you need some airflow. But the nice thing, as Yating said, we can control the airflow from 0 to any arbitrary value. So we can actually probe that scientifically, get resolution in regions we can't study on Earth at all. So it's very useful. So with that, I guess I'll take the next video. So we're burning stuff in space, and some of you may have seen this already. This is astronaut Tim Kopra. This is an earlier incarnation of our experiment where we were burning in this case, it was a plastic rod, a plexiglass rod. And I just want to point out the astronauts, very excited to be doing this. It turns out this is a very hands-on experiment. So we're talking with the astronaut, we're interacting with him, we're telling him what to do, how to set the parameters, and he in turn tells us, how it's looking, what he's experiencing. And as I said, the astronauts are very glad to do this. It's way outside their usual routine on a space station. So that helps us a lot because they're enthusiastic for our work, and they make very good investigators because of that. I could take the next slide, please. So this is a very simplified view of what differentiates our experiment from earlier combustion experiments. You can think of it as 3 parallel sheets. The 2 outer black ones are our walls, and in the middle is our fuel sample. It's sort of light gray. It could be either a cotton or a plastic. So the main idea here is we would have the astronauts change the spacing. We move the black walls in and out, and we could change the amount that the distance from the fuel sample to the walls, effectively making a narrow space or a wider space. As you heard earlier, the importance of the fire that we saw on Earth was a confined space. So we're looking at that effect on these flames. So our main variable will still be flow speed. We're going to change the fan, adjust the flow speed from 0 to 5, 10 centimeters per second. We also change now the gap spacing, so this is new for our experiment. And with that, I'll take the next video, please. So this is, again, an earlier experiment just to give you some idea of what these flames look like on orbit in zero gravity. On the left is a series of still images looking at the top of the in this case, a cotton sheet of fabric. And on the right is an edge view of that cotton fabric burning in space. So this is what the astronaut's seeing. Our chief data will be the images. We also have, you see the digital display above, relay some data, namely the time, the fan speed settings, and a radiometer to indicate the flame intensity. So we talk with the astronauts in real time. We can adjust the camera, which is nice. Usually the human eye is much better at picking up flames than the cameras. So the astronauts sometimes will say, we have a flame, and we don't see it with the cameras because it's much more sensitive. So again, it's exciting to do combustion off the planet. We've done it in space. We look forward to doing it for the first time ever on another world when we get back to the moon. It's sort of a watershed moment for humanity to think that fire is such an intrinsic part of our experience on Earth. So going way back to cavemen, of course, when they discovered and harness fire is a very big thing. So now we're finally talking about getting to the point where we're going to be looking at fires on other planets. So we're excited for that. So with that, I'll turn it over to you.
Right. Can we have the last video, please? Right. So the last thing, not the last, but another thing we would like to mention is that our microgravity experiment will be complemented by numerical modeling. Numerical model is powerful because it provides some example video here as shown here. Right. It provides great detail of the flame structure. Those, some parameter or some variable are not easy or not even available in the experiment. So yeah, that's how the model can help us. And those data can be used to help interpret the observed phenomena in experiment. Also, remember, this is a microgravity experiment. We don't have buoyancy flow, we don't have gravity. But with the model, if you can see the scale is relatively small. But with the model, we can always add back the buoyancy flow. We can always scale up once the model is validated. So the modeling will extend our finding, our result to more realistic scenario. And last, during the course of our project, the model will help to guide our experiment. So that's one thing we would like to mention. Thank you.
Excellent. So do we have any questions for our guests? Right back here.
Yeah, with these type of experiments, not just this one, some of these other experiments, what happens to that data? How accessible is that data? Is that for private use, or is that available for public domain for people to research against?
The idea for NASA has always been to make this as public as possible. Usually what we'll do is we'll give the first rights to analysis to the principal investigators, just sort of, for courtesy's sake. But shortly thereafter, the data becomes publicly available, and anybody can, data mine it or look at it or write papers using the same raw data. So it's exact same data.
Right. And actually, the video you show already on the database open to public.
That's right. The video is available publicly already. So.
Okay, we had a question right here in the middle.
Hi, so what's the process used to safely create an ignition in space?
Okay, so I probably should have said earlier, this is inside a glove box environment. So imagine a medical glove box where you put your gloves in, rubber sleeves to keep it isolated. So the astronauts have what they call a microgravity science glove box up there, and that's when you saw the video of the astronaut was looking at that glove box. So within this level of containment is our little device. So it's an additional level of containment. So the answer to your question is there's two levels of containment. So the flame is captive inside one device, which is then inside a second device. So that's actually redundancy. The flame has very little chance of escaping. So to get ignition, we simply use an igniter, electrically heated wire. So think of a glowing toaster element. If you get it hot enough, it sets anything pretty much on fire. So that's the way we get ignition.
Right. And another thing, as Dr. Fuku mentioned, right, without flow, it may even not be able to burn, right? So the worst thing we can do is just turn off the flow, and then things will quench, right?
Okay, we have time for one more question. Right back here.
So I know it's really early, and you're still doing the first test to then expand it and scale it up later. But how much bigger can this model and experiment become, especially attached to the space station?
That is a very good and hard question, right? So modeling, there are different techniques, right? So current model, the model, in-house model we use something called direct numerical simulation, meaning we model every single detail of the fire, right? So the good thing about this, for we capture all the physics, like small scale, right? But the bad thing is, I mean, not bad thing, the weakness is really hard to scale up, right? So right now, other models, say, for example, something called large eddy simulation, they have some submodel for detail. They just don't simulate the detail. They make assumption. So you lose the detail, but you capture the overall speaking phenomena. So to answer your question very shortly, that's something we're working on. So the scalability is always a hard question, right?
Well, let's give a nice round of applause for Professor Li Yao and Dr. Furkul. So this concludes our What's on Board briefing. We've had some great speakers here, so let's give them a big round of applause. And please follow us throughout the launch activities on www.nasa.gov/SpaceX. And coming up in 4 p.m. today, NASA will be having their pre-launch news conference for CRS-19 launch. Have a great day.